So I guess we should start with 5 minutes in. So welcome everyone. This is the fourth lecture in our MAG series, and today I'll be talking about the division algorithm in several variables. So I believe we've already talked about the division algorithm in one variable, and that's quite similar to how we divide integers by an integer by another integer, and that division algorithm for the polynomial ring in one variable was essentially the same. And I think that's ultimately because the polynomial ring in one variable is a principal ideal domain. And like the integers are also a principal ideal domain. I know I used this, but I didn't explain what domain was. It just means that every ideal is generated by can be generated by a single element. And so this is not true for several variables, so we'll see some differences and some extra complexity as we describe this algorithm and how it works here. So today I'm going to give us a description of the algorithm, what it does, and run through some examples of how to use this algorithm to divide polynomials, as well as say a few words about what conclusions we can draw about the main problems that we're interested in, which is a membership of ideals. And probably generation of ideals, but I think we'll focus on membership of ideals today. So to set up, I think I'll keep terminology, right? R is going to be polynomial ring in n variables, and I'll keep R and let n be implicit. So the idea is the same as in the one variable case, even though the algorithm is maybe slightly more complicated. We want to kill the leading term. And in the one variable case, we had a degree, and in several variables, Dan talked to us last week about monomial orderings, and we can use this to order the leading terms of monomials, right? So we're trying to kill the leading term. We can fix a monomial ordering, and then with respect to that ordering, we can kill the leading term. Okay, so I guess the idea, I'll write this down. So the idea is that we want to kill the leading term at each iteration. So I use this with the understanding that we're familiar with the division algorithm in one variable, and so this makes sense, and so we'll need monomial orders to decide which is the leading term. I guess to even define the leading term, right? Because what does leading term even mean, right? If you don't have an order. So I'll move over to the other board. So we'll divide. So the other complexity here is that, as you probably have seen on the other board, that we're not just going to be dividing a given polynomial by a single polynomial. We'll be dividing a given polynomial by multiple polynomials, and we'll see that this is something that we want to do because I guess it's because our ideals are generated by more than one element or more than one polynomial. So if we want to decide if, say, a given f is in an ideal generated by f1 to fs, we'd better divide by all of them at once, right? This wasn't a thing previously because previously all our ideals were generated by a single element. So to decide whether a given element is in an ideal, we just have to divide by kind of one thing, right? So so the other added complexity is that we'll divide a given f in R by several f1 to fs simultaneously. I guess, yeah, just at the same time. So the goal is to get an expression I guess I haven't mastered the art of talking and writing on an iPad at the same time. I guess when I'm writing on a board, it feels kind of natural. I feel like what I'm doing is I'm saying something and then I write the same thing and then I repeat it. Maybe it's not the worst thing in the world. Okay, so we want to get this expression where f is the given polynomial in R, and f1s and fs's, in your mind, this is the same notation that we've been using as generators for an ideal, right? F1 to fs, right? So that's what you should be thinking about. So we want to find an expression like this plus R, right? And so this is like the remainder, right? And these are like these f's, right? They're meant to be generators of an ideal. And of course, this is kind of meaningless, right? Of course, they generate an ideal. They generate whatever ideal they generate, but this is just something that we should keep in mind. And so we want to get an expression like this with a dichotomy where either R is zero, maybe I shouldn't say with, where either R is zero, right? Or the degree, well, now the next condition is a little bit longer, the state, where none of the monomials in R are divisible by the leading term of fi's. So none of the monomials, or maybe I should say, I'll say monomial summands, which makes sense. In R, so R is made up of a bunch of monomials added together. I just mean each of those monomials. None of the monomials in R are divisible by LTFI. I'll just put in brackets for any I. Slightly awkward phrasing. And the multi-degree of f is greater than or equal to multi-degree of f, aifi. And again, for any I, I'll just write for any I there. So when we write leading term and we write these, when we write leading term, it means we fix the monomial order. So maybe I'll probably say here, maybe here, I'll just write with respect to a fixed monomial order.
You probably want to assume AIFI is non-zero in the bottom line.
Yep. Yes. So maybe can I put it here? I'll write it. All right. So assume also. We want to assume. I'll put it in the same color. So we'll assume. Oh, AI. Sorry. Is that what you said?
Yeah, it's just in that last inequality.
Yeah. That's right. Oh man, I'm out of space. AI non-zero. Okay, thanks, Dan. I think I'm going to move back over to the division algorithm, and I'll talk about it, and I'll state the theorem that we want to prove, and then I'll prove the theorem. So just to give us a sense for where we're going, the theorem will be essentially that the division algorithm, as written out here, does what we want, which means it gives us that expression that I wrote in the previous board, and the output AI to AS and R will satisfy what we wrote on the last board. So let's take a quick look at the division algorithm here and see if we can understand what it's doing. So I've written this out previously, so I didn't have to do it now. So now I can just talk. So the inputs are f, right, which is a polynomial that we want to divide by, f1 to fs, and f1 to fs are the other inputs. And so we should think of the problem that we're trying to solve here is that we're given an ideal I generated by f1 to fs. We want to figure out if f is in it. We want to divide by f1 to fs. We want to see if r is 0. Now, of course, this is what we want to do. This algorithm will try to do that, but we'll see some problems that we'll run into as we go. And so we initialize the variables a1 to as because these are going to be our eventual outputs. These are going to be the things that will multiply by f1 to fs to give us our expression. And then we also have this auxiliary variable p equals thanks. I was wondering what is g. Does g appear again? Did I make this?
No, I don't think so.
I don't think it appears again. Thanks. Okay, so we set p right to be f, and we want to make f smaller and smaller and smaller. We'll make p smaller and smaller and smaller by dividing out terms successively using the elements f1 to fs. So while p is not equal to 0, so p is eventually going to die. We're going to pull off its terms one by one, and then we're going to go along the sequence of AIFIs, right? And we're going to firstly, if we find that the leading term of NFI divides P, we're going to pull it off. We're going to do this sequence of manipulations where we remove this from P.
You mean the leading term of P?
Exit the loop and keep going. Did I make a mistake again?
Well, you wrote divides P. What you meant is divides the leading term of P. Yeah.
It seems like I did some copying errors as I was going about copying this out of the book. So thanks, Dan. So I assume Dan, that's you doing it. Although this handwriting seems like it's somebody else. I don't know who's helping me here.
That's me with a mouse.
No one wants to own up to it? All right.
Oh,
that's fine.
Maybe.
So, right. So if we go through the loop and we find that P is unchanged, what this means is that none of the leading terms of the Fi is divided in the leading term of P. And so we're just going to rip off the leading term of P and throw in the remainder and go again, right? So this is a step that's new in this several variable case. This never happens in the one variable case. And here, if we find that when we go through the entire list of divisors f1 to fs that we cannot remove the leading term of P, we just shove it away in the remainder term and we keep going, right? And here we can already see something that we'll see in an actual example is that the order in which we divide by the f1 and fs may affect the answer, right? So it's not obvious whether it would, but it's also not clear at all whether it's independent of the order, right? So it will turn out in an example that whether r is 0 or not will depend on the order of f1 to fs. So and so once we're done with this, we're going to return A1 to AS and R. And the claim here is that this algorithm actually does what we want. So I'll write this up on another board. So let's walk over.
To be clear, R starts at 0, right?
R starts at 0, yes.
Right.
Yes. Did I not initialize it?
No, you didn't.
Oh,
but that's
sorry.
okay.
I should probably initialize it. Thanks. I guess Green Man is doing it for me. Thank you. Okay. I think
I don't know how to do your R's, Ken. Sorry. So I just did a normal one.
You know what? You guys gotta remember all the mistakes I made. I'm gonna buy some Roblox and give it to you. I think this will incentivize me to not mess it up so much.
Give me.
You can have that one, Eleanor. Even though I was going to say it the whole time.
Now, actually, before I give the statement of proof, let's do an example to make sure that we know how this goes. So let me check the old camera. Okay, so let's do an example, and we'll see how this actually works in practice. So this is an example right out of the book. I forgot what number it was, but probably you can find it. There are only a few in there. So f will be equal to x squared y. So now you guys are making me scared that these are all going to be wrong because I can't even copy out an algorithm correctly.
Don't worry. If they're wrong, we'll point it out.
Cool. You wonder how I get paid to write code. This one. All right. So how do we do this? We're gonna do this thing where we have a big fat division. What's this thing called? Do you guys know? I'm sure Dan knows. He's just keeping silent.
You just can't hear me. Can you hear me now?
Oh, I can now.
Yeah, no, earlier I was trying to speak and somehow you didn't hear me. I don't know what it's called. Radical?
Yeah, I guess it could be. I mean, that makes sense.
I actually don't
I
know
have
the
no
origin of this notation. That would be an interesting question. Like, why do we draw it with this
Yeah.
slight curve on the left-hand end, for example? Why isn't it just a corner?
Yeah, this is something that I've learned since I was young, and I've just done it without asking questions. So this is a good trivia question. You guys know the answer or find the answer by Googling it. I'll be interested to know. Okay, so this is how we typically set up a division with integers as well. We have this funny symbol that without a name, and but we have more things here, right? So we start with F1, and I hope we've written this out in the. So I actually forgot which order we're using for this. So I'm guessing we're using lexicographical ordering, but I guess it will be clear once we do it which order I'm using. So maybe this is a question that you guys can fill in, is like which order am I actually using when I do this division. So I look at and I see that x divides, so it's written out in this term, right? So I look at this term and this term, and I have x here, right? And so then I have to subtract, right? So I want to multiply x by f1, and I'm going to get x squared y, which is the same as the thing I underlined. And I'm going to get minus x. Nope, minus x. Minus x. And then we subtract. Okay, so this is doing the step in the loop, right? And we only do it with f1, and then we have to subtract, and then we start the loop again. We got exit the loop. We don't do it with f2 after we do it with f1, and so then you get x squared y squared plus x plus y squared. Now we're back to f1 again because we've found the leading term that it was able to kill, and so. Did I put this is a totally mistake, but I caught this, so that's certainly not
X squared, y squared? Yeah, okay. Damn, you beat me to it.
Yeah, because I was about to write it down and it didn't make any sense. So now we're back to F1, and I'm gonna erase this. So now we're looking at this term that we want to eliminate, and so then we multiply F1 by y, and so we do a plus y, and then we multiply F1 by y, and we should get the same thing here, and then we should get a plus y here, and then we subtract, and we should get some stuff. And the stuff that we get, that we're going to get x plus y squared plus y. So now,
it's minus y.
Oh God, this
Sorry.
is minus y. Well, you guys can keep a tab of this, right? The minus y. Yeah, you're right. So minus, that's why it's a plus on the next line. Okay, so now we're in a state where we try to eliminate the leading term. We cannot, because x, y, and y squared, well, none of them, you can't multiply them by anything to get x, right? So then what we do is we grab the x, we grab it and we chuck it into the remainder. So r is equal to x. And so we're gonna pretend that that's gone if I've circled it in red, and then we keep going. And so now what's left, right, is y squared plus y, and so leading terms here, and you can't eliminate this using x y minus 1. This is the first time this has happened, so we have to go to f2, and And when we go to f2, we say, well, this is just 1 times y squared minus 1. So we put a 1 here, and we put y squared minus 1 here. And then we subtract, and we get y plus 1. Okay. And so we can see actually that both y and 1, if we carry out the algorithm, I'm out of space, but if we carry out the division algorithm and we check the leading terms of f1 and f2, we can't eliminate y or y1. So both of these guys actually end up in the remainder, and we get plus y plus 1. And so after these calculations, what we get is that f, so the result is that a1, right? Well, a1 is going to be x plus y. a2 is equal to 1, and r is equal to x plus y plus 1. And we can check that this actually gives us what we want, right? F, right? So let's check, right? So check that f is equal to f1 a1 plus a2 f2 plus r, right? So what is this? So a1, so a1 f1. So this is equal to x plus y. f1 is equal to x y minus 1. a2 is 1, which I'll just write 1, and y squared minus 1 plus x plus y plus 1, right? And so this, when you expand it out, this should be equal to f, and f was whatever it was, x squared. F was x squared y plus x y squared plus y squared.
Just make one comment, Ken.
Yeah. So
back in the algorithm, I think your for loop on the topic of being paid to write code, your for loop seems that it would go through and look for f1 dividing the leading term, and then look for f2 dividing the leading term. You need a break, I guess. You mind if we pop back over there? I mean, what you actually did in the algorithm here is not quite what you wrote up. I mean, I think it doesn't make any difference in this example, but...
He did say break, right? He said exit for loop.
Oh, did he? Oh, I'm...
Got him!
Yeah.
So you have to give me Robux now, too.
Yeah. Wait. I have to pay up for verbal comments that are not absolutely correct as well.
That's a joke.
At this rate.
That's a joke.
well, you did make us walk all the way back here.
Yeah,
so,
that's true. Yeah, I deserve some punishment for that. That's fair. Okay, there was an exit for loop. Yeah, okay, good.
I didn't use break because I guess just in case people didn't know what it meant.
All right, that was some good exercise.
Yeah. Okay, so that was an example. I think I only made one sign error, which is amazing. So now we've seen an example of how this goes. We're gonna make a statement and try to prove it. So the statement is actually that the algorithm does what we want, and I'm gonna maybe how do I do this? So it'd be nice if I can refer to the fourth board over there. I'll just refer to the fourth board over there. So the theorem, probably not very nicely stated, is that the division algorithm described on boards 1 to 2 gives how do I say this? Output satisfying conditions on board 4. So unfortunately, this is I didn't want to write everything out again, right? So board 4 essentially means that says that you have this A1, A2 to AS and R, right? Such that either R is 0 or there's a bunch of conditions that the AIs and the Rs have to satisfy, things to do with degrees and divisibilities, right? So I won't rehash all that. I guess I'll restate all of that in the proof. And the division algorithm, I guess we've gone through it twice, I guess now, both in an example right here and in the first two boards. So hopefully it's not too much of a sin to just refer to the boards in this theorem. Okay, so I'll move
Ken,
over
I do
to
have one
third.
question about the conditions.
Yep.
So on the fourth board, there are sort of two conditions that you place on the output. One of them is on the remainder, which I think makes sense because it's analogous to the condition in the one variable case. But what about the condition on the A's, or the last thing where you say the multi-degree of F is greater than or equal to the multi-degree of AI, Fi, for all I?
Oh,
I wonder
yeah,
if that
see.
has an analog in the one variable case, because I can't quite see it.
That's just gonna be less than, right? Like literally, maybe that's just degree, right? Is that right?
Well, it
So-
doesn't really have an analog in the one variable case because you can't really trade off one divisor against another. I mean, the reason that's there is to stop you doing some naughty business where you for example,
Okay.
your example take like F, you take A1, I'm on the third board here. You take A1, you add F2 to it. But then you could also subtract F1 here.
Yeah.
And so you can do you can do business like that. Now, what you're doing there is you'll wreck the what am I trying to say? So
You might wreck the condition because F1, F2 as a product might have a higher degree than F.
Yeah. So
Okay, so we should just read it as like a nice minimality or something. Not necessarily strict minimality, but like sometimes it's nice to know that you do this in like an efficient way or something like that.
Yeah, it's probably a matter that it'll just become clearer from the proofs what role this plays. I think it's maybe not worth us trying to explain it beforehand. Let's come back to this. Yeah.
Cool.
And one more question.
Yep.
So we put a restriction that AI is not 0. Is that right? Or is it that condition holds where AI is not 0? Because it seems to me like if you were dividing F by several polynomials.
The condition wasn't that AI was non-zero. This was the bit I asked Kenneth to add. That's simply there because the multi-degree of AI Fi is undefined if AI Fi is 0.
So it's like AI could be 0, but if it's non-zero, then we have this multi-degree condition on that AI.
I guess strictly speaking, one of the FIs could be 0. So you do need the product to be non-zero.
Okay, clear.
So I should actually just change this to AI Fi non-zero. Fair enough. Yeah, it is. I guess it is undefined, isn't it? Yeah. Cool. Okay. Any other questions? Okay. So I want to prove this with a bunch of claims. So the first claim we're gonna make is that the algorithm terminates, right? Terminates. And so the proof is that so the polynomial P, right? So the polynomial P has finitely many terms. And you can already see where this is going. Each iteration removes a term from P. Either you remove it by finding an fi such that it divides the leading term, and then you do this algebraic manipulation to get rid of it. Or if you can't do this, you just forcibly remove it to R, right? So that's basically it. So on each iteration, the number of terms in P strictly decreases by 1. So then, of course, it terminates. So each iteration removes a term from P, and
Sorry, Ken, is that really what
Yeah,
we want to
so-
say? Count the number of terms? I think we want
I don't
to
think
say
that's true.
the leading term decreases in the monomial order. Even
Now, when you subtract y times fi, you might add terms.
Oh crap! You're right. Yeah. Yes. You're right. I guess. Yes. Yeah. You're right.
Well, the first
Do I
part
owe
is right.
Dan?
You owe the universe.
Yeah. So I guess each. I guess what I want to say. I guess each iteration sends P to lowers the order of P. Maybe that's the right thing to say. All right, decreases or decreases the order.
Well, let's not say order. Sorry to babysit you like this, but I mean, if we say order, that's not a term we've defined. You just mean it decreases the leading term in the monomial order.
Yeah, that's right. Yeah, LT of P, right, in order, right, and so eventually P, and so the term, so eventually the algorithm terminates at P equals 0, and since the order, eventually when you decrease the order, is bounded below by 0, and so it will terminate. So right.
Because the monomial order is the well order, right?
Yeah. Okay, so the second claim is that the output A1, AS, and R satisfies conditions on board 4. Right, so the proof, I guess I'm gonna kind of sketch this. So we're gonna use induction like in the one variable case. Remember the way, I actually don't remember whether we did the proof there, but how that proof goes is that you have the AIs and the FIs satisfying this. Well, we want to check that it satisfies, the equations. I guess the first thing we're going to check that it satisfies the equation. So I'm going to write down the equation F equals A1 F1 plus AS Fs plus R. I want to check that it satisfies this. Right? So start with, we're going to check that the initial. So I think we're going to check that the initial, the initial value is satisfied. But I'm now looking at this. I'm like, maybe the AIs was 0, right? What did I start R to be? I put R to be 0 as well, right? That doesn't make any sense. Hang on. So let's go back. So A is R. Okay, hang on. So give me 1 second.
No,
so we want to use
in the body of the proof you have plus P plus R, and then it's just at the end P is 0.
Oh, but body of the proof of the algorithm.
Yeah, so the thing you're going to prove by induction is true at every step, is that f is the sum over I, ai, fi plus p.
Oh, f is right. Plus p plus r, because that's okay.
And so initially that's true because p is f. Yeah.
Yeah, so I guess that must be the case, right? The only way you can balance out the equation is to stick a p in there. So this is use induction to show that the I guess AI AS RP satisfy. I guess I'll put a star here at every step. Okay, so I guess we've just kind of discussed this at the beginning, right? The AI is all 0, R is 0, P is F, so that's fine. And then there's some algebra you have to do for each of the loops, for each of the if conditions to check that this equation is preserved. And so I'll leave that as an exercise. So I guess the exercise is to check that the algorithm, well, I guess each loop preserves star. Okay, so I guess that's just algebraic manipulation. I guess you got to check that each loop and the initial values. Each loop and initial values preserves. I guess then it's preserve star, right? And then we have to check that the final condition, and I think I'm gonna also sketch this, right? So the final condition here is that either r is 0, right? So we assume that r is not 0, and we check this divisibility condition. So here a term gets added to r if and only if it's not divisible by any of the leading terms of the fi's, right? So here if you look at board 4, right, the condition is that none of the monomial summands are divisible by the leading terms of the fi. So this is kind of by design of the algorithm that if r has any terms in it, it can't be divisible by any of the fi's, right? So that's fine. And I guess the multi-degree condition, this is what we were talking about. I guess this is actually let me see. So the multi-degree of P decreases at each iteration, right? So I'm gonna maybe write here that, what should I write? So I'm gonna write the condition on R, right? So this is that, look at it again. So that none of the, that none of the summands of R are divisible by LTFI for any I. So I guess it's guaranteed by it's by construction, right? So it's by, I guess, a second if condition. Well, is that right? Yeah. So the second if condition only gets hit if you have a look at it again. So the first if condition checks all this stuff, and the second if condition, if P is unchanged, so So if none of the LTFI's divides any leading terms, then we throw into R, right? So second if condition. By the if conditions, I can't say if conditions. algorithm. And
I guess you could say it's by case analysis if you're being fancy, right?
yeah, I guess we basically checked it case by case, right, from the algorithm. Okay, so the last thing we have to check is that multi-degree condition, right? So the last thing there, so the multi-degree condition. So how do we prove this? So the multi-degree, so the multi-degree of P decreases at each iteration. Okay, so that's because we either remove a term, we can't escape this, right? We either find something to divide by and we remove a term, or we just remove a term. So the initial value of P is F, right? So each term of AI is some LTP LTFI, so multi-degree of AIFI is less than multi-degree of P. Maybe I should just write brackets, but I guess, yeah, multi-degree. I'll fix it. Of F. Okay, so I don't know whether this makes it clear. I think Eleanor, you asked a question before about what this condition was for, but I guess this is how you can see that this condition always holds with the way we do the algorithm. It's basically because AI is always of this form, and then you just kind of do these inequalities.
So do we want to say that AI is changing by the LTP divided by LTFI? That it will start off at 0 and it's changing by that expression you just had.
Yeah, right, because this is like at each iteration, right?
Yeah. I guess you could.
Yeah.
I guess what you meant was something like it's a sum of terms that look like that, right?
Right, it's formed from, right, it's...
Yeah, so whatever the leading term of it is, it's one of those. Or a sum of them that are the same monomial, I guess.
Remind me why each iteration decreases the leading term again. It's clear in the case where none of the FI's leading terms divide it, but in the other case, it's not immediately obvious to me.
I think we should probably just
So in the first if case.
Yeah. It's something you have to write out the expression to see.
Yeah, let's write it out on an export. Do we? Oh crap, we're out of space.
Yeah, an export's fine.
Yeah, let's go back. Yeah, so we go back to the algorithm, right? So you've got let me just reproduce a bit of that here so we can see it. So where were we? So we want to know the multi-degree of AIFI. Right, so I'm gonna rewrite some of this so that I have it in front of me so we can all see it. So this is the part of the algorithm where you divide. Right, so y is equal to LTP TFI here's AI, right? We want to add on this term, and P is P minus YFI, right? So that then we exit the loop. Okay, so we want to say that at each term of A, right? Let me see. So each term of AI is right. So we want to say that each term of AI is some LTP LTFI, right? So yeah, so because right, each time you do this loop, you're adding this thing onto there, right? So then, so the multi-degree of AIFI is yeah. So what do I want to say? So am I saying something obvious? So when you multiply this by FI, right?
I think Eleanor's question seemed to be related more to the P than the AIs. I don't know if anybody still has a question about the claim about the AIs. Is everybody clear on that, or is the question we should address
The
about
AIs
P?
make sense to me.
Yeah, I think the point of confusion remaining is to do with the P. So I think we can move on to that.
Oh, right. So because I wrote that the multi-degree of AIFI was less than the multi-degree of P. And
yeah,
I guess this...
the question was about
Is that strictly less?
No, that doesn't
Sorry,
have to be
as
strictly
well as
less.
I have a second question.
Yeah.
I mean, because you said it decreases in each iteration, right?
Yeah, so what
Oh, is
Eleanor's
that...
question was about the
because
fact
AI
that the leading term
yeah, I
of
see
P
now.
decreases.
Oh, P, right,
Yeah.
yeah. So I guess the decreases, right? So when you remove YIFI, is this not obvious? Because you remove...
Well, there's a step here where this is actually the crux of the definition of monomial order, this step, the second part, because we need to know that, okay, YIFI, so the leading term of, let's call it P prime, the thing on the left-hand side, right? Yeah, exactly what you're writing there, yeah. So P prime, what is its leading term? Well, it's one of the monomials that appears on the right-hand side. Now YFI, so if we take the leading term of P, we have to look at the leading term of the right-hand side. Look through all the monomials there. The largest monomial you see in that expression is the leading term of P. Now that's because, as Ken just wrote there, the leading term of YFI is the leading term of P. So there are no other monomials bigger than the leading term of P, and the coefficient of the leading term of P cancels out. So now, okay, that's clear, but why is it clear? I mean, you know in that expression P minus YFI that none of the monomials appearing in P can be bigger in the monomial order than the leading term of P, clearly. But why is it necessarily the case that in the YFI, somehow it couldn't have happened that when you multiply by Y, some monomial of Fi got bigger than the leading term of P? You know that leading term of P appears in YFI, but why couldn't it have been bigger? And that's the multiplication condition in the monomial order, right? So if you lay out the monomials of Fi in order, so from small to big, and the biggest one, leading term of Fi, is what you divided into leading term of P, and Y just shifts them all when you multiply. Right? That's what the second condition in monomial order says. It says that if you multiply by some monomial, and Y is a monomial, with a coefficient, so a term, when you multiply a polynomial by a term, it shifts sort of along, so to speak, all the monomials in the order. So you won't create anything bigger than the leading term of P when you multiply Fi by Y.
So it's funny. I finally understand what the question is because I always thought this was how can that possibly happen? Oh yeah, of course, Dan. Yeah, because what Dan said. Yeah, thanks. I totally thought that was obvious because I guess yeah, when you do it right, this will never happen, right? When you multiply by y, you're not gonna once you remove the first term, yeah. But multiplicativity is the key, right? Yeah.
Yeah, I guess it's sort of clear for the lexicographic order, which is why it seems obvious, but yeah, we are using that condition in general. Yeah.
Yeah. Cool. So I think this covers all of the conditions we mentioned on board number 4. So I guess I'm going to put a little box here to indicate the end of this proof. So the recap, the division algorithm does what we want, right? It gives us either R or it gives us and it gives us a bunch of AI satisfying these conditions, which these are going to be useful. So what am I supposed to stop saying? Or is that just in the chat?
They're talking about censored words. It's not important.
Okay, I thought it was about what I was saying. Okay, so
I was talking about you and Dan were both saying YIFI, and
oh yeah,
not
Really?
YFI.
Okay.
But you eventually stopped saying it after I said that.
oh right.
Does that count as an error?
Yeah, good question.
I don't know.
It's kind of
Yeah,
a typo.
so-
I think that's.
It'll be hilarious at the end of this to see how much
Oh, there's
how much
a-
Robux.
There's a running list in the Discord. You don't want to look.
Yeah.
Yeah, I don't think
this is hilarious.
I don't think pronouncing YI counts in my book. But
Okay, so I'm going to talk about some deficiencies of the division algorithm, because we already kind of alluded to this, but I'll kind of illustrate these with examples, and that's probably all we have time for today. Well, actually, all we have material for, not time. We still got half an hour left. so one, the remainder is not invariant with respect to permutation of devices. So the remainder. I guess I already kind of mentioned this, but this is an example. It's not, or depends on, I guess I'll say it in a less dumb way. May depend on the order of the devices F1, F2, F3, and so on. Devices. So we're gonna choose the same example, but as we did before, but with F1 and F2 swapped, right? And then we'll see that we get a slightly different R coming out from this. So if we remember the example, and this is not going to fit on the page because it already didn't fit before, and now I'm like kind of a quarter of the way down. So I'll write the example and do the division on the next board. So the example is F equals x squared y plus x y squared plus y squared. So F is the same. F1 is now what was F2, y squared minus 1, and F2 is now what was F1, xy minus 1. And so, yeah, so this is just the same example with F1 and F2 swapped around. And let's do the division and see what we get. Okay, so I'm going to maybe move this up so we can fit it. All right, so let's also make this a little bit longer. Oh, so like maybe while I'm writing this up, so how do I buy Robux? Is there like a store?
yeah, you can just go to roblox.com. But so metauni, the Roblox group, has a fair few Robux from what are called premium payouts. So people who come in here when they subscribe to Roblox, we get some, small number of Robux for every 10 minutes or whatever they spend wandering around in here, and that's added up over the year to some number of thousands of Robux, which is, I don't know, 30 cents or something in total. But So there's some Robux sitting there for me to pay out, so you don't need to worry about that.
I see.
I mean, if you make enough
So
errors,
Dan,
we'll run out. But
you're kind of far away, dude. Like I'm having trouble hearing you. Come closer.
oh yeah, I didn't follow the orb over here. Good.
Oh, so I think you were telling me that there's some bank that's obtained by people coming in and roaming around, and you get bonus Robux because of that.
Yeah, that's right. So there's some Robux
Oh,
sitting
that's
there
nice.
in that account that I can pay these fees out of. So don't worry about that. I mean,
If you want me to contribute.
you can't make 10 major errors per lecture, or I'll run out. But
We'll see. Okay, so thanks for that. So here's the same example as before with F1 and F2 replaced, swapped around, and so now we use y squared to try to eliminate x squared y, and so we multiplied. And we can't, right? Because y squared doesn't go into x squared y. So then we have to move along and go to the next one. And then this bit is probably the same as before, but then there'll be some changes, right, following this one. So x squared y. Yeah, I'm trying not make the same mistake. If I make the same mistake twice, hopefully I won't do that. That would be extremely stupid. Plus x plus y squared. Okay, so now previously we would have gone to x y minus 1 again, but now because we switched the order, now we use y squared, and here's where the thing is different. I use a different color. Now we multiply. Oh, I forgot to put x here. So A2, there's an x here. So now we go back to F1, we go back to the top of the list, and then we try to eliminate this term. Try to erase this, right? We try to eliminate this term, and so now we multiply F1 by x to get something that will work. And so this will be x squared y, xy squared minus x. And so when we subtract these two, you get 2x plus y squared, and now 2x is the leading term, and we see that neither y squared or xy would divide this, so we use the red to flip this over to the remainder, and now we have y squared, which we didn't see before, and now we go back to F1, and we can get rid of this, and we have y squared minus 1, and you get 1 remaining, and of course 1 is too small to be divided by anything in sight, so this also goes over here, and you get 2x plus 1. And of course there's a 1 here that, right. And so now we have completely different A1s and A2s and Rs, but this is also perfectly valid, and so so you get a different answer depending on what order you divide in, right? So here you've got A1 equals x plus 1, A2 equals x, and R is equal to 2x plus 1, right? So this is different. Sorry, so note is different from example 1. Oh, the previous example. I didn't number the examples. Previous example. Okay. So that's one deficiency, and you can already see this may lead to a situation where you divide in one order and you get 0, and you divide using a different ordering of F1, F2s to FSs, and you do not get 0. But you know that if you have an equation f equals ai fi all summed up, right? That's sufficient for f to be in the ideal generated by f1 and fs. But we see that it's not necessary, right? So this is I'll
just
show
to
this example
reiterate
as
that
well.
a bit. Yeah, it's worth noting that in the one variable case, the remainder is unique, and therefore the quotient is also unique, right? So you can talk about the remainder and the quotient. Now, the algorithm that we've defined is an algorithm, it's deterministic, so if you fix the order of the FIs, you'll get the same remainder in quotients, the AIs, that's what I mean by quotients. You'll get the same remainder in quotients every time, but they depend on the ordering, potentially, at least as we understand so far in the course.
Yep, cool. So I'll just, I guess for emphasis, I'll write this out one more time, right? So the remainder term equals 0 is sufficient. I guess R equals 0 is sufficient. Is a sufficient condition for F to be in F1, Fs, but not necessary. All right, so because, as Dan said, the remainder is not unique, right? So there are many possible remainders coming from different permutations of F1s to Fs's and possibly different choices of generators as well. We only need 1 0 to occur in this world for ideal membership to be verified, right? But so the strategy is not to check all possible bases. We're gonna culminate. This will culminate to us picking good bases where we can actually verify ideal membership by dividing by these bases. This is the Grabner basis that will come and next week. Is that when we're defining Grabner bases? I guess maybe there's not yet. Yeah, I guess next week is like Dixon's number maybe. So at some point we'll define a special basis where we can rely on it to give us a condition for checking whether something isn't an ideal by checking that the remainder term on division by this basis is 0. So one more example, which
Sorry, before you go on, I want to ask Billy what his question was. I'm reading it, but I don't understand it. Can you permute the FI every step and get something sensible? Oh, I see. Yeah, that would
Can you
work.
change your mind about the order of them as you go?
There's lots of variations on the division algorithm, so that would make sense. You could do that, no problem.
Like permute, not randomly though, like in a specific way.
No, I mean every loop through the algorithm, you could look at the FIs in a different order, and that would be different to both of the calculations you just did. Well, in principle, in general.
Yeah.
It'd still satisfy. I mean, somehow it counts as a division algorithm if the form you get at the end is right. So the F is the sum over i's, ai's, fi's plus a remainder, and you have that multi-degree condition. Then do whatever you like. So yeah, that in particular would work. You can also kind of average over the divisions, so you can try and divide by all the FIs at once by looking for all of them that have a leading term dividing the leading term of F or P, and then you subtract. You sort of average over them and subtract, all of them at once.
Can average. Oh, like that.
Yeah. We've actually. My student Spencer's used that in his thesis. That's another trick you can do. So there's lots of variations on the division algorithm, which is funny. I mean, in one variable, I don't think there is any useful variant, but in multiple variables, there certainly is. Yeah, it's a good question.
Cool. Okay, so last example, it's not going to fit here, so I'll just go with behind. That's convenient. These are the only boards that are reversible?
The other set, the last set of boards also has a back, but those are the only two that are reversible so far, yeah.
I see. Cool. So the last example, I guess, is like this. It's kind of similar to what we wrote before, but F is different. And the F2 is xy plus 1. So what I've written here is that I want to note first that that f is equal to x times y squared minus 1, right? So f is actually in the ideal generated by f1 and f2. It's actually in the ideal generated by f1, but to be pedantic, I guess we write the whole thing. But I'm going to show you that on division of f by f1 and f2 in that order, we're going to get a non-zero remainder, right? So so getting so it's not necessary to have a zero remainder to have having a zero remainder is not a necessary condition of ideal membership. So so this is an easier division because it's short. So x squared y minus x, we're going to divide it by f1 and f2, so it's y squared. Why is it that in my notes these are swapped? f2, f1. I'm going to do it the way I have it in my notes, so it's not completely screwed. So xy plus 1. So I guess either way, right? We're going to do it with some order. So we're going to multiply by y. Wait, did I write this? No, see, nobody caught this. Or maybe someone did catch it and just didn't tell me. X squared y, not xy squared, not x squared y. Okay.
He's nervous.
So,
He's losing money.
Wait, did I catch this, or did someone else catch this?
Nah, they didn't. They were too slow for you.
I guess I only realized when I tried to divide them, like that doesn't work. So right now is fine. We kill the first term. Y times xy is xy squared, so that's gone. And what's left is 2x. And the 2x goes in the remainder because it's not divisible by any of the leading terms there. This goes into R, so this is 2x. And so, so we have a non-zero, right?
I think the reason you did it backwards is because if f1 and f2 are what you say they are, then it does divide fine.
Oh, of course, right? Because
so you got f1 and f2 backwards, and then you fixed it later, but you didn't fix it again.
Oh yeah, because I wrote f1 and f2, and it really should be f2 f. Oh no, there is a line where I switched them. Okay, sorry, that's fine. So basically, if we divide f2 first, and then f1. I didn't label them. I just wrote them down, right? So technically, it's not wrong. So basically, punchline is that R is non-zero, but F is in F1, F2. So R equals 0 is not necessary for this to be true. It's not necessary for this to be true. Okay, so I think that's it for today for the division algorithm. So hopefully we saw some examples, and I think the exercises will have plenty of these. It's just very easy to write questions for these. And I think, any questions? I'm gonna check the Discord.
Ken, are you sure that xy plus 1 times y is xy plus x?
X what? Xy plus... Oh, what?
Is that not xy squared plus y?
God, are you serious?
I'm so sorry.
How can this be so wrong?
I'm so sorry.
No, it's good. It's good. I think I must be either drunk when I make my notes, or I'm drunk now. But I don't think I'm drunk now, so it's probably when I make my notes. Thanks. Is that right?
At least it's non-zero.
Yeah, I think that's good. Yeah, it's not 0 and it looks plausible.
Well, yeah, if that was 0 too, then I'm truly screwed. But yeah, it's still 0. It's non-zero, so it's very easy to be non-zero, right? Most things are non-zero. So.
No, great. That was despite the amusing errors, that was very clear. Thanks.
Thank you.
I'd never seen this before, and it all made sense. So we got there.
Yeah, this was kind of a surprise to me too when I read through it. When I read through it the first time. So yeah, interesting chapter.
Yeah, it's a much less simple operation than the one variable case, right? Not only because it's multiple polynomials and multiple variables, but it really is a genuinely more interesting procedure.
So Dan, or Dan or Ken, I asked him because he pointed this out at the start. If you did do the thing where you had an order and F1 greater than F2 ... if you like extended the monomial order that way, then we still have problem 2, but we don't have problem 1, right? There's a canonical remainder, but if it's non-zero, you might still be in the ideal.
Right. Yeah.
Well, I mean, you could say it's canonical, I suppose, but there's nothing more special about that.
Canonical, if you right, sure. What I mean is, sorry, if you fix an order, there is one true answer, but we still have problem number 2, right?
Yeah, I suppose, but there's nothing more interesting or magic about that ordering than any other particular ordering you pick. It just doesn't have any status. So, yeah.
Makes sense.
Yeah, it's interesting that these issues are hints of a deeper piece of mathematics that we just don't have in our hands yet, and that's the notion of a Grosvenor basis, which is genuinely one of the most important advances this concept is a very important advance in sort of 20th century mathematics to articulate this. So it's meant to look like multivariable division is a bit wonky and probably doesn't work quite right when you first see it. And that's a hint of actually something deep that we haven't seen yet, namely Grosvenor bases.
So you said that this is like a fundamentally more intricate algorithm because of those two reasons. There's the sort of the dependence of the remainder on the generators that you pick, and there's the fact that you're kind of juggling multiple polynomials that you're dividing by at any one time. So the Grosvenor basis will fix the first of those, so we'll get the remainder property that we want. But I think you can, it seems to me, I mentioned this at the start, you could probably do the division of multiple polynomials by first dividing by the first polynomial and then dividing the remainder by the second polynomial and then repeating that. And that seems like that would be a lot closer to the one variable case, that division algorithm by a single multivariable polynomial. All you have to do now is
you could do that.
Remainder terms that you take up halfway through.
But then you'd have to go back to the beginning and divide by f1 again. Because there's no reason that you would have eliminated all the things divisible by the leading term of f1 that you couldn't get from any other leading term. So you could structure the division algorithm in that way, though, where, as it was written and as it's usually done, you'd attempt to divide f1 into it, and then you go back to the beginning and you try f1 again, and if it doesn't work, you do f2. But then back at the beginning of the loop, you try f1 again immediately, right? You could... if we thought about trying to just keep dividing by f1, do all the f1s first, you say. Well, you divide by f1, you go back to the beginning, you try dividing by f1, that's what you're already doing, right? You will keep dividing by f1 until you get to some point where no monomial, the leading term is not divisible by the leading term of f1. Then you'll look at f2, but once you've done that step, you may have created something now. You may have switched the leading term of the dividend, p, to be divisible by the leading term of f1 again. Now you could say, I don't care, I'm done with f1, leave me alone, and you could keep dividing f2 into it. That'd be fine. That would correspond to what Billy was saying, right? You'd just be switching your order of the divisors at that point. And you divide by f2, and you keep going, and then you run out of things that f2 divides into, or rather the leading term is no longer divisible by the leading term of f2, and you go on. But once you get to the end of the list, you still may not have those conditions until you go back and sort of clean up by doing f1 again, and so on.
Until you can no longer do any of them.
That's right, yeah.
Yeah, that's clear.